Mutations are sudden changes to the nucleotide sequence or nucleotide base sequence in DNA. So they can come about because of the influence of a number of different factors. They can come about spontaneously and unexpectedly. And what they're going to do is they're going to change in some capacity the sequence, the base sequence of DNA, and possibly lead to different amino acids being put in place in protein synthesis as a result of the changed DNA sequence. And that can lead to poorly produced proteins and then problems in organisms down the track. So mutations can sometimes have no effect, but mutations often can have negative effects on organisms. So we're going to look here at a number of different changes that can occur in a base sequence of DNA, which can lead to varying types of mutation, varying changes in amino acid sequences of a protein. So first of all, we're going to have a look at a missense mutation. So a missense mutation happens when, sometimes we call it a substitution mutation, happens when we get a change in the base sequence of DNA by having one base swapped out for another. So what you notice here for each of these ones, what I'm going to have, each of the examples, I'm going to have an original DNA, and then I'm going to have mDNA, so that's going to be the mutated DNA, so the DNA that has changed because of this particular type of mutation, which here we're talking about a missense. Like I said, sometimes we've got a substitution. And then similarly, I'm going to have the original desired amino acid structure or sequence, and then how that's going to affect the mutated amino acid sequence. So how the amino acid sequence would change if we get a DNA mutation. So DNA mutations come about when the DNA replicates as well. So when our DNA tries to create an exact copy of itself, we might get the wrong base being used when that replication occurs. So what I've put in here is we've had a substitution. So everything is the same going from this DNA to the mutated DNA, except our T has now become a G. So we've had that swapped out. So our CTC stays the same, and our GTG stays the same. So the original amino acids here, CTC programs for leucine, GTG programs for valine, they won't change. So we don't have an issue with those. However, the TTT changing to a TGT means that we now have the amino acid cysteine in its place. So what we see in substitution mutations is we usually get one amino acid changing to a different one. So this can then affect protein structure and folding and have an incorrectly made protein because the binding is not able to occur between particular amino acids which would have otherwise, because we've now got to change the amino acid in a particular position. Same sense mutations come about in the same kind of way. What we'll see is we'll see a substitution. So you should have already noticed that I've put in a particular substitution there, but see if you can pick up how this is a little bit different to the previous type of mutation going on the amino acid sequence, or the mutated amino acid sequence. So what I've done is, what's occurred in this type of mutation, it is a substitution mutation, but we call it same sense instead of a missense. There we call it same sense because this T swapping to a C doesn't actually affect the amino acid being programmed for. So our sequence of TTT, CTC, GTG, which gives us phenylalanine, leucine, and valine. Leucine and valine stay the same because the sequence hasn't changed. The T swapping to the C, luckily for the organism, still programs for the same amino acid because there's numerous DNA triplets and mRNA codons that program for the same amino acid, up to sort of 4 or 5 in some cases. So that's a same sense, or a silent, sometimes you call it silent mutation. We get a substitution that doesn't actually affect the amino acid in that slot. Next up, we have something called a nonsense mutation. So in a nonsense mutation, what we might see is a sequence which continues on. There was no error. It's correctly transcribed till we get to this point here. So TGT has now become TGA. So our T has been swapped out for an A. And in a nonsense mutation, this will have quite a large effect. So where we did have cysteine being programmed or being formed there, we now have a stop codon. So in a nonsense mutation, it doesn't only change up an amino acid, but it can terminate the building of a protein from an amino acid sequence early. So nonsense throws it right out of whack, and we stop building this protein early on because we get a change from amino acid like cysteine to a stop codon, and we stop building that polypeptide chain altogether. So that can be have a quite drastic effect on an organism. Last topic I'm going to talk about is frame shift mutation. So frame shift mutations can have a bit more of an impact than our substitution, so missense, especially more than our nonsense. Our missense and our same sense mutations. Frame shift will have a lot more impact than a missense, and definitely a lot more than a same sense, because same sense is, like I said, silent, doesn't change the actual amino acid sequence. Alright, anyway, so if we have a look at a frame shift mutation, this is an insertion. So what's going to happen is a base will just be plugged in and inserted in our sequence that shouldn't have been there in the first place. So we're going to have a sequence here, TTT, and now I'll do it like this. So I have C, T, C, C, T, C, T, G. All right, cool. So what you'll notice here is, I'll pop in the extra one first. So we're going to have an A inserted here. What you'll notice is that this sequence is the same to here and the same to here. And then our C has just moved down a slot. Our T has moved along a slot. Our C, there, T, and our G, like so. So what's happened is this A being inserted there has meant that all of these particular bases have actually moved down one space. So we call this a frame shift because now these sort of triplets that are being read, and the amino acids are being placed in a polypeptide chain as a result of these triplets, now are all going to be pushed along one, and our sort of nice little frames, our groups of threes, get out of whack. So what you can see here is TTT is still going to be phenylalanine in our mutated amino acid structure, but now we have threonine instead of leucine. If we go along to the next one, our cysteine has now been changed to leucine. So what we've had happen is this amino acid has now changed, but then every amino acid has the potential from that point on to change because everything's being pushed across or pushed along, and we've now got this kind of concertina effect where every amino acid down the line is going to be affected by that insertion. Some of those sequences might be same sense. We might get lucky in where the sequence doesn't change the amino acid, but a lot of them are going to change. So it's going to have quite a big effect. Very, very similarly, if we have something like this happen where we have a deletion, we might have GTA, something like this occur where our T's are all good, but what you notice now is we've removed the C at the start of our second triplet there, which has caused everything to move along like so, and this C has actually gone in our deletion. So we've removed completely a base, which then is going to have a similar effect where we see our phenylalanine is still going to be there because of our TTT was unaffected, but then our leucine has now become serine, our cysteine has now become valine, and so on. So we get this frame shift, this concertina effect of changing amino acids down the line. So those are some types of mutation that can come about because of changes, spontaneous changes in the base sequence of DNA when replication makes mistakes and gets things wrong.